All right.
You
Well,
know,
by my clock, it's 3:35. Does that sound good if we get going?
yeah, let's do it.
Well, I before I hand it over, I just wanted to say that we've been looking forward to this presentation for a while. Mark and his team did an amazing job of compiling a huge amount of information on this very kind of contentious subject of carbon and how you count it in buildings. And how you look at sort of narratives around forest management and other things. And this was completed some time ago, but Mark and his team are so in demand that we haven't actually been able to pin them down to do this presentation until now. So I really appreciate you, Mark, and your team being here to do this, and looking forward to hearing you present. So I'm going to just pass it straight over without further ado.
Yeah, thanks, Ian. So yeah, this is not the full team, but we've got a really strong member of the team with us today, Ethan Bloom, who was a huge contributor to this project when he was a student at U of O, doing his MS, and now is doing great things at FFA. So I really am happy that he can join us today because he did all the graphics in this book and that we'll show coming up, and was a huge contributor. Also, just a disclaimer that this is really like enough content to fill, like a whole term seminar, and we're trying to condense it down into a meetup. So really, there's so much there. We spent several years working on this, and so we're going to try and give the highlights today. And then direct you to more information that is part of that project on our website. So just a little background, I guess, introduction for those of you that don't know me. I know many of you on this call. Mark Fretz. I am an assistant professor in the Department of Architecture and also co-direct our Institute for Health in the Built Environment, which has a lab in Eugene and Portland, and we've been doing a lot of mass timber research with that group over the years. And we started this in 2020, which is hard to believe. It's just been a long time. Uh, so, at the time, we were all very interested in performing, and we still are, whole building life cycle assessments. And there are all kinds of different materials that go into those assessments. And as designers, you get to choose those materials and have an impact on the carbon profile of buildings. Yet there were a lot of different narratives out there from different industry groups that were confusing. And some of those narratives included, for instance, that steel is infinitely recyclable, or concrete is durable and never gets taken down, lasts forever. Or whatever it may be, we were getting a lot of different narratives. And so that's why we called this project Carbon Narratives for Design Planning, because we wanted to try and sort those out using scholarly literature and experts in the field, to be able to come to hopefully some consensus about these different materials that we're using. So also around 2018 to 2019, my co-PI, Professor Allison Kwok, who unfortunately can't be here today, was working on a project benchmarking embodied carbon in different mass timber buildings, again using whole building life cycle assessments. And I was working with students in a class that I have called Design the Unseen, doing similar carbon studies. And we both recognized that depending on the analysis tool that you used, and the database for those tools, we could get vastly different results for biogenic carbon. And that's the carbon associated with living materials, such as harvested wood products. So when we asked professionals in the design community, we also found that there was a general sense of confusion and uncertainty of those results as well, mainly from the mass timber building life cycle assessments due to the biogenic carbon, which got us thinking that we needed to really investigate more and really harness the diverse expertise of those in academia, industry, nonprofits, government groups who are working on these issues to try and hopefully sort these things out. So this is, again, a large group effort. We've got Ethan here today. He was a huge contributor, but also Allison Kwok was a co-PI, Kevin Vanden Wymelenberg, and then several other students. We worked with Quorum on this project, as well as many guest presenters that contributed to this. So when we first wrote this grant, this was a grant that was then ultimately funded by the USDA ARS through Tallwood. And when we first wrote this grant, we had this idea that we would get everybody in a room in person for a big workshop, and we were fortunate to receive the grant, and then COVID hit. And so our workshop idea in person, sorting things out together in a room, was tabled, and we ended up doing something a little differently to approach this. We started with a survey that was sent to architects, engineers, contractors, manufacturers, government organizations, nonprofits, and academics, wide-ranging groups there to try and figure out the current state of knowledge in 2020. We got 305 responses back, 180 of which were from the AEC community across North America. And the results of the survey then informed the basis for bringing together these different panels of experts that had a diversity of perspectives. They weren't all on the same page all the time. So we really wanted to foster this discussion from these different groups. So we had 5 different workshops that were hosted online, and those are still on our website. So I encourage you, they're about 2 hours each. So if you have time, I encourage you to go to our website, either at the Institute for Health and the Built Environment or on the NetZED lab website, to access these. So you can watch those different workshops and the presentations by those panelists, pulling apart some of these issues that were a bit pervasive at the time. So that also, those workshops also served as the basis for further literature review, and we use those in to kind of dig deeper into these topics, and then develop ultimately this graphic field guide for design practitioners and students that we could use for well, things like this, or for seminars that we could structure around this content. This is another kind of major output of this grant. This is the design guide. Ethan did the graphics for this. I encourage you to check it out. It's really great, and on our website as well. Also on the NetZED Labs website, and I think Tallwood's website will get this soon once they get their new website up and running. But again, this integrates hundreds of scholarly articles that we reviewed. In fact, this one's got over 250 sources that are cited in this document, and it's presented in a graphical format. So we think it's rather engaging, not, and not on just pages of text. So really great for designers to take a look at. So that is kind of the context of this project. And, since this project occurred, there have been many great buildings that have gone up, that, the PDX airport, for one, that's really been doing amazing work with, with mass timber wood products and track and trace, and a lot of things that have gone on since we started this. So I'm going to just kind of start in by giving an overview, then I'm going to hand it over to Ethan to talk about some of these components. So first of all, embodied carbon, why it matters, why do we care? Well, for one, the global building stock is increasing rapidly. It's expected to double, in fact, by in its current floor area by 2060. So that means we're building a lot, and construction currently represents about 40% of global annual anthropogenic greenhouse gas emissions. 27% are from operational emissions in buildings. That's, emissions used to heat, cool, power a building. And over the last few decades, there have been significant improvements to reduce these operational emissions through more efficient, equipment and better envelopes, passive strategies. But unlike operational emissions, embodied emissions, so those emissions that are associated with the materials that we use in our buildings, those are emissions that occur in a very short time span during the manufacture of the materials for a building and its construction, and are so-called locked into that building for its lifespan. So once those occur, they're in that building, and there's no opportunity to further reduce those over time, like we can do with operational emissions as the grid, the power grid gets less carbon intensive. So in in this project, we're looking at different um, stages. This is if you look at that graph on the right, the life cycle assessment, there are different um, stages of a life cycle of the life cycle, and the product stage is what we're typically looking at in a lot of the assessments that we're doing, but also the construction stage, use stage, end of life, and beyond life are important contributors to the entire story. So I'm going to hand it to Ethan to talk about structural systems.
You. So, when we're talking about embodied carbon, I think as designers or others working on buildings, it's important for us to recognize structural systems and the way that we optimize them as the leverage point to significantly reduce embodied carbon, particularly because in mid to high-rise construction, the superstructure of a building alone can drive up to nearly 80% of that building's entire embodied carbon. And when we are looking at material choices for these kind of superstructures, we're often focusing on either mass timber, concrete, or steel. And when you compare the three at face value, timber often presents itself as the lowest carbon alternative, mainly because as a bio-based material, it's renewable, it's relatively less energy intensive to produce, but it also stores carbon during plant growth. And this makes timber a really powerful tool for climate change mitigation. But it does have some caveats that I'll address in a little bit. But ultimately, most structural systems are going to incorporate some mix of all three materials. And so really understanding the carbon implications for each is important to use them judiciously. And so the next several slides will look at the opportunities and barriers for both concrete and then steel in terms of decarbonization. And I want to preface that while these two industries are generally considered hard to decarbonize, they do offer or present significant opportunities for further decarbonization. I think that the problem is without radical shifts, the barriers and limitations that they do face will continue to steer them off track from meaningful mid-century emissions reductions. Next slide. So getting into concrete, concrete is the most used building material globally. It's also highly extractive as it relies heavily on the use of sand, for which there is a global shortage of which is driven primarily by concrete production. It represents about 8% of global annual greenhouse gas emissions, and nearly all of these emissions stem from cement production, but more specifically to form clinker within cement production, which can drive upwards of 90% of cement's total emissions. And so at the core of the concrete industry's emissions is clinker. Lime is a staple ingredient in ordinary Portland cement. And to get lime, immense heat is needed to heat limestone within the kiln. This is often supplied by fossil fuels. Sorry, the lights are motion activated and are not. There we go. Limestone is heated by fossil fuels. This represents about 40% of cement emissions, but the remaining 60% of emissions stem from limestone calcination, which is a natural chemical reaction where heat drives CO2 from calcium carbonate to leave lime. Next slide. And so one of the most common practices today to substantially reduce emissions associated with cement are through the inclusion of supplementary cementitious materials. These are materials that look to partially replace the amount of lime and clinker content. These are often limited by availability or the extent to which they can replace lime before affecting structural properties. And for some, such as fly ash or blast furnace slag, these are byproducts of already carbon-intensive processes. And so their substitution in cement mixes their benefits may be overstated from a carbon perspective. To address the energy used for kiln heating. There's also been research into alternative fuels such as biomass or industrial waste. And while these can provide modest emissions reductions, the main concern lies with the burning profile characteristics of these fuels within the kiln and how that might affect clinker properties. And then there's also been research into novel binders and recycled concrete aggregate. These are often don't make it past the laboratory phase, but novel binders look to replace limestone entirely. But these are often hindered by the need for reform of building code and design practices, and they're also associated with higher processing costs, expensive additives, or even unproven supply chains. And then kind of similar for recycled concrete aggregate, which looks to preserve virgin or natural aggregate with the use of demolished concrete. The main limitations are in terms of performance concerns and the variability of quality, although a number of studies have found that this sort of sweet spot to replace natural aggregate is around 30–35% before you start to see a decline in structural performance. Next slide. And so to wrap up concrete, I think when we talk about concrete, an often overlooked blind spot is concrete's potential as a permanent long-term engineered carbon sink. Through carbonation, exposed concrete surfaces will reabsorb atmospheric CO2 through diffusion, and then that starts to fill in the microstructure of the exposed concrete with calcite products. The diffusion rates depend on a number of ambient conditions, but ultimately carbonation is a very, very slow process. And LCAs, which use 50 or 100-year time horizons, they struggle with how to credit those removals in time periods beyond that. A number of studies do point out, though, that the carbonation benefits of concrete, LCAs that exclude them might be understating carbonation benefits by as much as 20–30% of initial emissions. Still, concrete emissions are instantaneous, whereas carbonation is slowly over decades, and carbonation will never offset the initial amount of emissions. So concrete, unfortunately, still remains a net emitter of emissions, and the benefits of carbonation are, I guess, less beneficial or applicable to new construction. Next slide, please. And so moving on to steel, it accounts for about 7% of global greenhouse gas emissions. And at the core of the industry's emissions is the use of coke in iron making within the blast furnace. And so for context, most surface level iron exists as iron oxides, which is essentially rust. Iron ore needs to be stripped of oxygen in the blast furnace, which produces a molten pig iron. This pig iron, however, is unusable because it's still highly dissolved with carbon, and structural steel needs a metallic iron that's more stronger and more ductile. And so kind of counterintuitively, this molten pig iron will move into the basic oxygen furnace where pure oxygen is blown through it, further dissolving the carbon content from what was 4% to down to 2%. And other alloying elements might be included here for other certain desired structural properties. But this is considered the traditional steel making method, and it accounts for about 3/4 of global steel production. And on average, produces just over 2 metric tons of CO2 per ton of steel. The most efficient, blast furnace, basic oxygen furnace systems might get it down to about 1.8 tons of CO2 per ton of steel. But the reason why this method remains so commonplace is because it is the one route that can accept iron ore as a main input. And generally, high grade quality steel is often associated or comes from iron ore. Next slide. And so an alternative to reduce steel's embodied carbon is alternate process methods. The second main alternative is through the electric arc furnace, which accounts for about the remaining 1/4 of global steel production. It runs on electricity and can produce just shy of 1/2 ton of CO2 per ton of crude steel it produces. Its main inputs are recycled steel scrap, but it'll also accept direct reduced iron. And so direct reduced iron is essentially iron ore chemically stripped of its oxygen within its solid state, skipping the liquefaction that you'd see in the blast furnace, and produces a sort of sponge iron that can then be fed into the electric arc furnace. And if you were to pair direct reduced iron with the electric arc furnace, it can achieve crude steel with just 60% the carbon footprint of traditional steel making. If you were to use hydrogen as a clean energy carrier for the direct reduced iron equipment and use that alongside the electric arc furnace, it can come down close to net zero emissions. And so on paper, the electric arc furnace seems like the way to go, and very promising, but the reason why its use is so limited is because it can't accept iron ore as a main input. And I'll talk about the reason, more on the next slide, but because it can't accept iron ore and it depends on steel scrap, there is limited availability of steel scrap. And steel scrap often produces a lower quality grade steel. Next slide. And so a really big pro to steel is that it does have high recycling potential and as such has developed strong end-of-life markets because of it. One of the real main barriers, though, is that most steel is currently locked in current infrastructure. And so there is limited availability of steel scrap, and this warrants the production of virgin steel with iron ore. And again, iron ore can only be processed in a blast furnace, which is much more carbon intensive, but also commonplace. Recycling steel also often contains residual contaminants such as chromium, nickel, copper, tin. These are harder to remove metallurgically when remelting, and so it makes reprocessing difficult each time it's recycled. And it can affect negatively the structural properties of the new steel. So I think recycling steel will become a key strategy moving forward for steel industry, but it requires improved sorting and collection methods, particularly in other parts of the world where steel scrap might be, going underutilized, or if it's happening at all. Next slide. And then lastly, for steel, what's considered the sort of game changer for the industry is the use of hydrogen as a clean energy carrier. It exists in large quantities as water, and its byproduct is simply water vapor rather than a greenhouse gas. The environmental benefit of hydrogen as a reducing agent in iron making will depend a lot on the way that it's produced. And so there's been colors that dub hydrogen based off the way that it's procured. Gray hydrogen is hydrogen that's derived from unabated fossil fuels. Blue hydrogen from abated fossil fuels with carbon capture technology. And then green hydrogen, or in other words, clean hydrogen, stems from water electrolysis combined with the use of renewable energies. But the success of hydrogen as a clean energy carrier will depend on its feasibility to scale up and mend the infrastructure gap. So green hydrogen, at first is already more costly than the use of fossil fuels. It would also require a huge electrical demand, and therefore a large expansion of renewable energy. Hydrogen as an element is also a very tiny molecule that can easily leak. And so it requires high pressures and low temperatures, making storage, transport, and handling challenging. And so I had mentioned earlier that when you use hydrogen with the electric arc furnace, it can bring close to net zero emissions. Again, that only represents about a quarter of global steel production. I think where hydrogen would shine best is where there is a need to produce virgin steel from iron ore. The problem is that the blast furnace, basic oxygen furnace route is not so easily switchable to hydrogen. It would require a lot of capital investment to sort of refix these methods. But it's also the really heavy hitting hotspot where hydrogen would work best. Next slide. So back to timber, I had mentioned earlier that timber presents itself as the lowest carbon material, but timber is only sustainable if the forest management behind it is as well. And I won't get too much into the, what sustainable forest management means, because I think it means a lot of different things, and the definition will change depending on who you ask. Different forest managers prioritize different goals. But I think at the very least, it should ensure that forests remain forests, but also help to improve forest resilience as, amidst directional climate change, where it's crucial to carbon dynamics. Next slide. And so speaking of, forest carbon dynamics are driven in large part by disturbances. Increasing frequency and severity of disturbances are evident in many forest ecosystems globally. And a warming climate alone could lead to extensive tree mortality over time, as seen in the case of drought, where induced moisture stress can surpass plant physiological thresholds, leading to tree die-off. The same warmer and drier conditions that induce drought can also spur positive feedback loops that reinforce the next wildfire or insect outbreaks. And these disturbances can cause large-scale tree mortality within a relatively short amount of time. These all impact, forest vegetation growth, reproduction, survival, and distribution. And because this is carbon narratives, from a carbon perspective, can also significantly alter forest net primary productivity. Net primary productivity is the net amount of carbon that a forest fixes through photosynthesis minus the carbon it releases via respiration. And it's a key measure to how much carbon forests store, but it's also an indicator of how much biological activity they support. And so disturbances disrupt net primary productivity, but forest resilience and the capacity for forest regeneration will determine whether it rebounds, shifts to a new regime, or declines long-term. Next slide. And so it's really important to emphasize and improve on forest resilience, which is the ability of forests to recover post-disturbance. And a lot of the ways that forests manifest forest resilience is through disturbance legacies. These are the physical and biological markers, traits, species adaptations are features that are left behind in a forest post-disturbance. And so these can include deadwood, root systems, surviving plants, seeds, spores, animal populations, surviving plants. All these act as a sort of memory bank of the pre-disturbance forest, and they carry forward the ingredients that make recovery possible. And so disturbance legacies help to facilitate regeneration, ensuring that forests regrow faster and effectively than if the area had to recolonize from scratch. They maintain biodiversity, supporting a diverse ecosystem through the recovery period. And what's really important is that they also enable adaptation to future disturbances, improving the forest's ability to cope with repeated or novel stresses. And I think this is really where the concern lies, is because climate-driven disturbances now will likely catalyze rapid reorganization of forests through a series of abrupt and episodic events which can erode the ecological memory of forests to disturbances. This can create a resilience debt that then shapes forest trajectories, determining whether they'll remain forests or some other type of land use. Next slide. And so I think an important way to achieve forest resilience is by using more efficiently rather than extensively, so as to ensure that forests remain forests via an increased safe operating space. By increasing that buffer of what we harvest versus what we leave intact, it maintains natural regeneration and productivity, ensuring that forests don't lose the ecological engine that allows sustainable yield. Protecting biodiversity and ecosystem functions works within the contextual bounds of forests. It avoids overharvest, but maintains genetic diversity. And also just working to grow resilient forests reduces the risk that timber supply collapses after an extreme event, thereby supporting long-term carbon storage and wood yield. Yeah, I think next slide.
Okay. Yeah, so life cycle assessment, or LCA, is a really important tool for us to be able to compare what we're designing with, alternate designs and benchmark buildings. So it also reminds me of this old quote from George Box that all models are wrong, but some are useful. And actually, I think these LCAs are extremely useful, but we should also recognize that they're complex assumptions from these really dynamic systems that are going into these models, and so that's where things start to get a bit complicated. So we often hear that, the wood is carbon neutral because it's a renewable bio-based material, which will be replaced by another tree, sequestering its associated carbon after it's extracted. But carbon neutrality does not always equal climate neutrality based on timescale. So carbon neutrality makes several assumptions, such as steady state forest regrowth, and it can also discount the complexity of emissions and sequestration. So being carbon neutral does not mean that we will necessarily meet climate goals, which are climate neutral, because those emissions occurring now may not have enough time to be offset as we try to target the drawdown within the next few decades. So that temporal aspect is important. Climate neutral considers that the timing of carbon fluxes varied with time horizons, cycles of forest regrowth, and disturbance risks, for example. So if tree mortality accelerates, sequestration assumptions may be too optimistic. So those are a few of the things that need to be considered. So to allow time for offset of carbon emissions, harvested wood products should be converted into building products that are long-lived. That's important. Harvesting trees solely for bioenergy production is an example of a wood product that's not being necessarily climate neutral, even though it would be carbon neutral, since this would produce more immediate atmospheric carbon during the period in which we must be reducing the atmospheric carbon to meet climate goals, and has to do with the longer time scale required for that carbon reuptake to be considered. So that's an important consideration as we think about selecting materials and using them in a way that allows their long life and durability. We began the project again in part due to the widely variable LCA outputs, and therefore the uncertainty in the models that designers were encountering when especially examining the bio-based building materials due to the biogenic carbon, which is known as the module D component for LCA. We've since learned that modeling carbon flows is difficult, and it requires large models that make assumptions and inputs from other large models. For this reason, many current LCA tools use a backward-looking approach to assess carbon sequestration. So the kind of the traditional LCA looks backward to assess carbon sequestration preceding harvest, with the tree attributed to a timber product as the tree being harvested. So this produces a result that shows carbon sequestration in a product up until the point of use. So if you look at that figure on the left, you'll see all that sequestration happening, and then that's when that carbon credit gets taken place when that's harvested and used as a material. Whereas dynamic LCA, which is the one on the right, is more forward-looking, and it captures the carbon story a bit more accurately than traditional LCA by using that forward-looking approach to model carbon sequestration, because it takes into account the building life cycle emissions and forest regrowth simultaneously. However, it's currently more difficult for designers to employ with the tools that are available. And the project highlighted the fact that current tools that are available to designers also do not use regionally specific forestry data, which is a current shortfall that we hope will be improved in tools over time for sourcing decisions. So moving into more timber cities, into developing and growing timber cities. Ethan, I'll let you talk about substitution benefits.
Sure. Yeah. So, up until this point, kind of tying everything together, assuming that we're sourcing our timber from sustainable forest management, being good stewards of forests, we can now really maximize the benefits of timber as a bio-based material. And that starts with substitution benefits. So the choice alone to use a lower carbon material like timber in place of a higher embodied carbon material like concrete or steel provides immediate emission savings, which is crucial, again, from a climate neutral perspective to address near-term mid-century reduction goals or targets. Some might argue that substitution benefits for timber are overstated because in LCAs, they don't allow enough time for other industries to decarbonize. But the same can be said for the timber industry, which is always looking to better improve. And also, again, we're concerned with near-term reduction targets. A lot of LCAs that compare timber products to concrete or steel counterparts in a wide array of varying contexts oftentimes show timber with the lower global warming potential. And so substitution provides immediate emission savings. You can then extend the benefits of timber to longer term emission savings through carbon storage. The carbon storage benefit of a timber product improves the longer it secures carbon away from the atmosphere. And so some might vouch for maximizing forest carbon because forests can sequester and store much more carbon for much longer than buildings can. This only creates a one-time benefit of carbon storage, and mature forests will eventually saturate and their rate of carbon uptake will plateau as carbon uptake is eventually balanced by plant respiration and decomposition. And ultimately, it leaves these major carbon sinks, these very saturated forests, susceptible to disturbance risks, which can turn them into carbon sources. On the other hand, maximizing carbon in both forests and the built environment, working with steady state forestry, where new stands of forest maintain or even surpass the carbon levels of the forest that preceded it. You can then begin to allocate into carbon into the built environment and create a continued benefit or contribution to carbon storage that maximizes the overall land sink. Yeah.
So as we transition to timber cities, we can have a significant reduction in carbon emissions by 2100 based on the studies that we found. One of the studies that we found pretty important was by Mishra et al. In 2022, which found that if 90% of the population lived in timber cities by the end of this century, this could realize a 77% reduction in atmospheric carbon over business as usual approaches. So part of that, though, requires sustainable forest management and keeping forests as forests to realize these benefits. And also, we need to be mindful that wood products are produced with sustainable forest management, as Ethan talked about earlier, and that we maintain strong governance and careful planning to protect frontier forests and biodiversity hotspots. According to Mishra et al., in addition to protecting frontier forests, this transition would also require an increase in trees and an increase in global forest plantation areas, which is still possible with land use for other agricultural food production processes. So that was their finding, and the paper was pretty influential in our ultimate findings to this project. So wood product certification and chain of custody are also important for designers to feel confident that their material selection is what they expect. So with that, I think we can give kind of the main takeaways that we had for this project. We had a lot of different takeaways, but the top takeaways from the project were that, first of all, global building stock is expected to double, and we're building, by 2060, we're building a lot. So it doesn't matter whether we're using, timber, steel, or concrete. All materials have impacts, and we need to be careful with how we use them. Buildings account for 40% of global CO2 emissions. So therefore, we've got a role to play in mitigating climate change as designers, and can really focus on the system that we're using. Embodied carbon becomes locked in today's building projects and cannot be reduced over time like operational carbon. So we really need to be mindful of that during the design process. And building structural systems are the largest source of embodied carbon in a project, up to 80%. So really focus first on the structural materials, which will have the greatest embodied carbon impact. And those structural materials that are bio-based, such as mass timber, offer a potential solution to mitigate these embodied carbon emissions. The quickest means to reduce global warming potential at the material level, though, is to use materials and all materials efficiently, and therefore use less of them. So reuse existing structures is a great way to do that. Reuse existing materials, substitute carbon-intensive materials derived from fossil fuels with low carbon materials. And then the long-term climate benefit of timber products improves the longer biogenic carbon is stored away from the atmosphere, so that new trees have the opportunity to grow and sequester more of that carbon dioxide in the atmosphere before those return to the atmosphere. So that means that we need to be designing buildings that are designed for durability, for longevity, designed to be disassembled and reused at their end of life, because all of that will improve the carbon story. Furthermore, we should also select products that convert and use biogenic mill waste into long-term architectural materials. So I'm a big fan of wood fiber insulation. That's one of those materials, for instance, that converts that. And those are a few of the initial takeaways. I'll let Ethan talk about a few others.
Yeah, and then, kind of back to the forestry aspect of it, letting trees mature without harvest would only create a one-time benefit of carbon storage. Active forestry does have a place in creating a continued contribution to carbon storage. And this also kind of creates a paradigm shift where, from buildings as carbon sources to buildings as a carbon sink. This is particularly true for the transition to timber cities. And a lot of modeling studies often see timber as a viable climate change mitigation solution because of its lower global warming potential. But I urge designers to maybe interrogate or at least better understand LCA assumptions. Because again, biogenic carbon, it's very complex. We touched on it a little bit with dynamic LCA, which looks to paint a more holistic understanding of the carbon story for wood products. But again, there's still a lot of unknowns. There's still a lot of uncertainties in how to accurately model or account for it. And so just being aware of those assumptions that you see in your EPDs or, whatever, kind of would help you make better decisions for sourcing and procurement of wood. Yeah, and then again, most structural systems are going to use a mix of all three materials. I'd gone over a little bit the implications for each, but finding the best ways to optimize each of them for a very carbon efficient structure can make meaningful embodied carbon reductions for your project.
So with that, I think what we're going to do is we're going to shift gears and ask Blaine to present and then take questions at the end so we can kind of integrate both of those projects. But again, this was enough material. This was the highlight, but enough material for a whole semester seminar. And so you should go to our website and look at the full document which has even more content in there.
Yeah, there definitely was a lot that we did not get to cover, but.
So Blaine, I'll see if you can share your screen.
All right, wait a moment, please. That carbon narratives is just a great source to understand the complexities of carbon. And so what I'll be sharing with you is not nearly as complex. So I urge you to keep in mind all of the caveats that are really neutral viewed towards mass timber when you watch what I have to show you. One moment, getting the sharing going. And here we go. All right, do you see this?
Almost.
Almost.
It's coming. There we go.
All right. So I'm going to shift focus a little bit. And while the carbon narratives really focused on the broad scale integration of mass timber into big construction at wide, I was interested in actually looking at a different kind of comparison, which is how mass timber really measures up in its related construction system considerations to lightwood frame conventional systems for low-rise residential construction, something where mass timber is not as focused, rightfully so at this point. But first of all, I'd like to thank you all for being here. My name's Blaine. Sorry, I forgot to introduce myself. I'm a recent graduate of University of Oregon's Master of Architecture, Master of Science of Architecture programs. And what I'll be showing you today pertains to my Master of Science terminal research project, which had to do with mass timber design in the residential sector and covers carbon analytics with some of the analyses that I'd conducted. So the project, I named it BioMod, and it looks into the applications of local species CLT and forest products in modular housing for the northeastern United States. Oh, there we go. So the main objective of this project really was to devise a panelized mass timber housing system for single-family residential application, which prioritizes the use of biogenic materials and a reduction of necessary finishes beyond the structural elements. After which, the idea was to compare my design system between two other cases of relevant conventional construction typologies. On one side, the BioMod design system was to be compared with the current typical construction typology within the modular housing industry itself. And on the other side, I wanted to see how the biogenic mass timber system compared with conventional lightwood frame construction and its associated common practice material palette. So overall, the project was comprised of three main parts, being background research, the design of the BioMod system, and analyses, where several areas of performance characteristics and quantitative metrics were looked into. For the purpose of our discussion, though, I'm just going to mostly focus on giving you a general overview of the BioMod design system itself, providing some background, and of course, the comparative analyses of embodied carbon that had performed between the three construction systems. So let's get into it. To begin, the focus area of the project is really formed around three primary motives, which are to portray the use of locally made mass timber for the northeastern United States specifically, demonstrate the benefits of biogenic materials in buildings, a place where carbon plays a key role, and support the rural housing sector and forestry in the region. So from those motives, as well as through the background research I pursued, it was ultimately determined that my project would focus on designing single-family modular housing using eastern white pine as the tree of choice for mass timber in this project. It's all hypothetical. I would then, of course, conduct a series of comparative analyses between my design system and the related conventional systems in an effort to reveal the potential competitive advantages of biogenic mass timber assemblies in low-rise residential application. So I did also look into several volumetric and panelized modular mass timber home case studies that already exist in North America, which is very promising because it supports the notion that there is some degree of interest for mass timber integration into the low-rise and mid-rise residential building sectors. Notice how all the opal shelter in Maine are located on the West Coast, and it goes to show just how much more established the momentum here is for mass timber out this way in this sector. So Mark and Ethan very clearly touched on carbon in the built environment and why is it so important. Architecture 2030, 2023 actually updated the quantity metrics of the total embodied carbon in the built environment up to 42%, with about 15% being related to construction materials and their fabrication. So the quantity of the pie has only gone up since the 2022 metrics, which is only even more of increasing concern. And it's a big deal because we're seeing more frequent and extreme climate events, and carbon emissions, of course, are a primary culprit of that. Various ways we can really work to reduce carbon impacts of the building sector is decreasing operational energy demand through properly designed enclosures, prioritizing renewable source carbon sequestering materials, and sourcing them locally to reduce transportation-related emissions. So this project pertains to modular homes, and the general modular home industry looks like this, where modular homes are just another common housing solution beyond standard site-built houses in the Northeast and the United States as a whole. These homes are prefabricated off-site, and they're shipped in whole volumes to be stitched together on the site. After this, however, the volumes have been taken off their steel shipping chassis so that they can be treated as a standard home as far as codes go. And their construction assemblies are also much like that of new construction conventional site-built homes, which consist primarily of materials from non-renewable sources beyond their structural members, several of which may be adverse to occupant health, and many of these materials, though, are not necessarily dependent on the structural typology, but are simply the industry standard materials of choice at this time. Things like fiberglass insulation, gypsum wallboard, those kind of things. So where could mass timber products come into play with this modular industry to make improvements? Well, as biogenic engineered products that can take the form of large structural panels, such as cross-laminated timber, a mass timber constructed home could reduce materials usually associated with being needed to cover up light wood framing. It could derive a house proportionally made from more renewable material mass, and of course, sequester more carbon. This is a result of being physically more massive fiber taken out from the forest, so keep that in mind. If CLT were also produced locally instead of being imported, it could create rural jobs and reduce the carbon emissions and costs related to that distant transport. So those are really some of the general conditions that the project set out to respond to. Now let's see what mass timber could actually do in action in this sector. So the biomod system is what I devised, and it's an additive panelized mass timber modular design for single family dwellings once again. And it works on an 8-foot wide CLT panel module, which can be easily shipped and evenly divided into smaller parts when necessary. It's a system designed for expandability, where the construction assembly and module layout enables aggregation, and so do the construction details, which I won't be showing today. With this in mind, a panelized modular system was chosen over a volumetric one because it allows for greater flexibility in variable expansion, as well as for its efficiency shipping the parts. In this case, the assembly panels are designed to have the insulation, weather-resistant membranes, and furring prefabricated to the CLT panels before they reach the construction site, after which the exterior cladding is then attached, and this would really increase the efficiency of the panelized modular construction by reducing the time needed for on-site assembly, which would in turn save on labor costs, construction emissions, and reduce potential error caused in the field. In case you're wondering about the architectural form, now's a good time to say that the biomod system was designed to be rooted in the Northeast. I know we're in the Pacific Northwest, whose vernacular principles are really generally centered around a compact form and gable roof, which are most appropriate for the drastic swing in winter and summer climates in that region. These formal principles would aid in optimizing the energy efficiency of these homes. So through iteration, it was determined that this system would work on a defined 28-foot width, with expandability being focused on one axis. At 28 feet, the layout provides an organization of a centralized 4-foot circulation datum flanked by two 12-foot bays, dimension that's typically deemed accurate and adequate in providing comfortable living space. The starter home is the base condition of the design system, where predetermined space modules are organized into a functioning home. With an interior floor area of roughly 672 square feet, the starter home expresses the intention by which biomod houses are designed to be relatively compact, in order to lower overall footprint of the home to reduce initial costs, ongoing energy demands, and total embodied carbon of the construction. As mentioned, these houses are designed to be expandable as part of the modular system, and so what this allows for is that it helps to support aging in place, where individual households and families can be able to grow within a home that can grow alongside them. This really helps to form and retain genuine communities, lower the vacancy rate of housing, all of which enables a mindset for society to hopefully focus on long-term investment and care, a place where mass timber would have the greatest advantage. With the ability of a biomod house to start small and grow later, this reduces the initial cost barrier from home buyers, as well as our forests up front. As for shipping, the efficiencies achieved as a result of the panelized modular system of 8-foot wide panels, where the components of a house can simply be flat packed on a standard semi-truck and brought to the site. This really helps to avoid the carbon emission penalties associated with oversized load shipping, for instance. We need pilot cars in some scenarios. And the pieces of the starter home, for instance, could all fit on a single semi-truck, after which 2 or 3 semi-trucks would be required to ship a whole larger house at once. I guess this doesn't include the windows and the doors that would also need to be shipped. All right, looking at a theoretical manufacturing chain real quick. Almost all materials above the house, above grade, comes from timber, and so the CLT material would optimistically be sourced from sustainably harvested eastern white pine, where it would be produced at a CLT production facility located directly in the Northeast. Obviously, this doesn't exist yet, And forest products would then make their way to a production facility where the biomod house panels and kits would be prefabricated. Once at the production plant, the biomod homes would ideally be produced in a volume of standardized units, which is also the method in which current manufactured and modular homes are brought to the market. This aids in driving down unit cost, making a mass timber construction system relatively more affordable. And as the design is comprised primarily by renewable biogenic material, the system could possibly function at a closed loop of efficiency in the long run in a perfect world. So this all comes together again to form a home that's designed to be compact but feels spacious at the same time, while also reducing the need for finished materials, yet improving biophilic qualities of interior living space. All right, so I hope that provided a good enough overview, it probably did, of what the house design is. So finally, let's get into looking at the carbon narrative between the mass timber system and the conventional ones. To begin, the various analyses are structured in an organized and consistent fashion, where a representative typical modular house that I designated through background research is set against the representative biomod mass timber house, which is in the center, as well as a standard conventional lightwood frame constructed version of the biomod house design is then compared on the right. Mouthful. Keep in mind that the typical modular house model is larger in square footage than the biomod house and its lightwood frame constituent. This is intentional because the system that I derived have smaller footprints for the same type of home, being 3-bedroom, 2 bathrooms in this case, which is the average sized home in the Northeast. So again, we'll mostly just be focusing on carbon analyses that I did through life cycle assessments. Before I go further though, it's very important to note that the project boundary for the studies to come do not include every aspect and component to the whole construction of a home. Instead, the aspects that remain relatively consistent as part of each building system's character definition is kept in the project boundary, whereas the components that would easily fluctuate in character and method are not included. So this does mean that the foundations and the steel fasteners are excluded from these studies, amongst other things, which of course would affect the end results of a true construction type. So this is a typical modular house assembly. It's a lightwood frame constructed system with an unheated, ventilated attic roof structure. As you see, almost all the materials that go beyond structural framing and sheathing are made from non-renewable source materials, as the typical industry standard material choice. Looking at the proposed mass timber home, the opposite is true, where almost all materials come from renewable sources, being trees in this case. Different from the typical modular house, the attic space is now included as a loft level within the conditioned space. I guess I'd like to point out at this point that this is located in the Northeast, so wildfire is not necessarily as big of a concern as to why I have wood cladding on this home. And so looking at the last system, the same formal method for the lightwood frame version of the design remains true. The system shares the same cladding and ground floor elements as the mass timber house, so because they're not directly dependent on which structural system is used. This was to keep everything even. So the prong of analyses that we're focusing on, of course, is the life cycle assessments, which will map out the carbon emissions and global warming potential of each building system using the traditional life cycle assessment system. So I used one-click LCA software as the analysis tool of choice, where I did my best to select the most appropriate environmental product declaration within the platform for each material. Various LCA scenarios were mapped out in order to get the big picture of each system's embodied carbon characteristics within the study boundary. And it's important to note that for the purpose of this analysis, transportation-related carbon and repair percentages and operational energy were omitted, as those could vary amongst each system. In one-click LCA 60-year benchmark score assessment on the left here, it just provides a little snapshot, and even so, the biomod house wins as the most sustainable construction type in terms of carbon emission. But let's see just how. So a cradle-to-gate assessment analyzes the carbon of a building only up to the point of when they reach the construction site. This is useful because it displays only the amount of carbon simply inherent in the building materials themselves. This graph shows each system's total initial carbon emissions by the time the materials reach the construction site, but this does not yet consider the inherent biogenic carbon stored in some of the materials involved. So if we fold in the biogenic carbon, you can see that the sequestered amount between the two, light wood frame systems and the mass timber system, are pretty significantly different, with, of course, the mass timber with just a sheer amount more volume and mass of fiber is storing a lot more carbon. So why is biogenic carbon important at all? Well, this is carbon that's been pulled, of course, from the atmosphere and held within the structure of an organic substance or plant during its life. And so in terms of construction, these are the materials that represent the embodied amount of carbon previously pulled from the atmosphere and is now banked within the building. So in short, having biogenic carbon stored in a building can help delay the rate at which carbon would be re-released into the atmosphere if it were left as a plant to naturally decay, which can be a great advantage in delaying or reversing the effects of climate change. The longer a building with biogenic carbon can last, the longer it can actually sequester that carbon, which is why the need to build longer lasting buildings and housing stocks is important now more than ever. Bottom line, if you want to use biogenic carbon as an advantage, you better make sure that the structural system can last longer than the tree will remain standing in any given forest stand. Anyways, next we'll be looking at the total carbon footprint through a cradle to grave over a long period of time, 100 years. So I've instilled the data of carbon emissions for each system after 30 years, 60 years, and 100 years. One thing to keep in mind is that the structural materials of each system were not given a service life, so we're going to assume that all three homes would last for a century regardless. So let's look into some of the details over time of why those numbers were so high. So after just 30 years, the typical modular house has added 16 more tons of carbon to its total emissions, which doubles its amount. And it's a result of the replacement of materials that are needed due to them reaching the end of their service life. This is the wall finishes, floor covering finishes, and the asphalt roofing at this point. You'll see that B4, B5 material replacement section on that top carbon contribution pie get larger and larger as a trend, as this represents all the service lives that are being replaced throughout time. So after 60 years, the total amount of carbon emitted by the typical modular house is about triple of its original amount. It's almost 49 tons. There have already been 20 instances of material replacements at this time, with materials like the nylon carpet needing to have been replaced 3 times and the entire house repainted 5 times. These are all defined by the service lives in the EPDs. And after 100 years, the typical modular house has established that it's a construction system that features a lot of short-lived finished materials currently that generate significant contributions in waste and carbon emissions on our planet. Material replacement is now responsible for over 2/3 of the building's carbon footprint, which are concentrated in the floor finishings and coverings, as well as wall and ceiling finishes. This indicates that an intense use of covering finishes may not be the best for our future construction systems. So if we look at a mass timber home, after 30 years, just about nothing has changed from its original state, save for the considered carbon related to the construction process. There's no need for a material replacement at this time. That might be a testament to the reduced amount of finished materials in the construction. By year 60, the all-wood exterior cladding, of course, is needed to have been replaced, which now adds around 6 tons of carbon to its initial 11 tons emitted. And after 100 years, the mass timber home's total carbon emission has not even reached 20 tons. This is good, relatively. Material replacement is relatively minimal, with only exterior cladding elements needing replacement. This is the advantage of reducing the need for finished materials in a construction system. And now we'll run through the standard constructed house of the same design. Similar to the typical modular house, the interior finishes had to have been replaced, adding 5 tons. After 60 years, just like the biomod house, the mass timber one, all the exterior wood cladding had to be replaced. And after 100 years, there's been 24 material replacement instances and over 20 added tons of CO2 applied to the initial state of this system. So that is all considering, not considering biogenic carbon. Now let's recall upon the biogenic carbon and factor these back in. So with biogenic carbon considered in each system, you can see how each of them actually starts out as net negative in terms of overall carbon when they were first constructed. However, the typical modular house very quickly crosses the net zero threshold by year 30, with the standard constructed house following by year 60. After these respective points, both the lightwood frame construction systems and their industry standard material choices are contributing to the problem of global warming instead of combating it. The mass timber home, with biogenic finishes on the other hand, remains well under the net zero carbon line even after 100 years. Over this time, the home's embodied carbon has only risen from negative 54 tons to negative 45. That's 9 added tons, which can suggest that under very, very perfect conditions, perhaps in a vacuum, this construction system can remain carbon negative for another 400 years. So, in short, the qualities that a biogenic mass timber constructed housing system would allow for is less frequent material replacement and a much longer lifespan for successfully sequestering carbon. As for the other two construction systems, it goes to show just how important the material choices beyond structural elements have on the total impact of a finished construction characteristic with carbon in the low-rise residential construction sector. Something else to keep in mind, however, is how much more mass of material goes into making a mass timber house compared to a standard lightwood frame. The same design in mass timber would require almost 2 times the amount of mass. This, of course, would require the mass timber home to have a slightly costlier foundation, but it also demands much more from the forest in any one given mass timber home than a lightwood frame home. This is why sustainable forestry and resilience in our forest sector is very important. And it's paramount that a mass timber construction system remains standing for the long run to make the most of its perceived advantages in durability. And now, one last thing to leave you with, though, is a quick suggestive difference in labor intensity between a mass timber panel system and a lightwood frame one. So let's look specifically at the characteristic difference between the number of pieces in a CLT system versus a lightwood frame system within a construction envelope. If we focus on just an 8-foot section of a solid wall, you'll see that the lightwood frame wall, studs spaced 16 inches on center, would require about 10 members to be installed, whereas the CLT created section is just a single piece. Now, if we introduce an opening for something like a window, the lightwood frame wall jumps up to 22 pieces in order to properly frame an opening for a window and the whole wall, where again, the CLT wall is just a single piece. You can see how this general condition really aggregates to a dramatic difference in the total number of pieces in construction between a panelized mass timber house and a lightwood frame house. Additionally, the pieces of CLT left over from being cut for a window could be reused to make partitions, shelving, and doors, which is what's actually done in the biomod house design. This all equates to labor intensity and on-site construction intensity over time. So when it comes to mass timber integration within the single-family residential sector, I found that there's many aspects to consider for its competitiveness against conventional lightwood frame. Neither is right or wrong. I think it depends on the vision and the values of each individual developer. However, what is shown at least is that there are true advantages of long-term carbon sequestration, material renewability, and construction efficiency of a biogenic panelized mass timber modular housing system. Such a mouthful. By utilizing structural panels instead of sticks, the resultant construction system will require fewer layers in the assembly, bringing with it the benefits of having fewer finished materials needed in need for regular replacement and fewer material resource streams, especially if you're using a biogenic based insulation. While I didn't cover every performance topic that I'd analyzed in my research today, these are my generalized findings of the entire project. And to sum it up, there are considerable long-term benefits of a biogenic mass timber construction system to give it competitive potential with conventional systems. Cost, of course, is a factor that I've not mentioned much through this project, and it's really very important. Very important. But in general, it can be understood that the mass timber modular house would require more expense up front compared to the conventional systems, but can see its investment potentially paid off with superior durability, energy efficiency, and health for the environment and households in the long run. Future studies would definitely benefit from including cost comparisons, as well as inputs of foundation and steel connections within the project boundary. And that's what I have for you. A PDF of the entire project and findings can be found on my LinkedIn, and I'm always happy to share But thank you so much for attending and listening in.
Thank you, Blaine.
Yep.
I think we have some time to take questions if there are questions.
Mark, I have one to kick off on the carbon narrative side of things. Um, it's been a little time since you did the report. What kind of feedback have you been getting, and kind of from whom? And have you been getting any kind of pushback, or has it been positive? People learning new things? Just curious.
Yeah, I mean, I haven't gotten any negative pushback. I've gotten good feedback, especially, I mean, we've used that with students quite a bit in the classroom. And so that's primarily where I've gotten feedback, and it's because it's so graphic. I think it's really a descriptive report. But I haven't heard any negative pushback, and I think it's because we had so many different stakeholders at the table all along throughout the process. So we did get pushback throughout the workshops with different, viewpoints that we brought together, and that was intentional that we brought these different stakeholders together to be able to try and find out where the kind of the sore spots were that we had to get more information and use literature to help kind of overcome some of those. So I think once we had all of that, the final report seemed to be well received. Ethan, have you heard anything?
No, I haven't really received any word, but I know that while we were doing this, one of our kind of concerns was that, I think ultimately you might piss someone off, but I mean, it is trying to take an unbiased kind of neutral perspective. So, yeah.
Thank you. I see
Yeah.
Mark D'Onofrio has posted a question in the chat.
I mean, I guess, yeah, as far as how do we specify, these materials with kind of considering all these nuances, I guess, making yourself more aware about the nuances and then maybe bringing it to the manufacturer, asking these questions. They may or may not give you answers on how far up the supply chain it works, but I think it's just worth kind of prodding these kind of nuances.
I think one of the things that came out of this, from all the workshops and the work that we did was that if you're sourcing wood in North America, it's generally going to be good. It will be good. We can always find ways to incrementally improve, what we're doing. But some of the supply chain issues really come into play when wood is being sourced from some of the areas abroad that don't practice the sustainable management of their forests. So, being mindful of supply chains and chain of custody is important. The certifications that are out there help with that. I know, that ZGF did a lot of that with that research with the Port of Portland's airport, which was kind of concurrent and after we did this work. So there's been a lot of work that's been done since this project started.
Can I throw another question in there? Sorry to be
Yeah.
greedy here, but this is for Blaine. And Blaine, I'm really impressed by the depth of your analysis there. Like, amazing work. I haven't heard about this before, but I would, just really great project. When you compared the kind of carbon impacts of the three kind of house typologies, and you have that sort of what you call the typical modular house, and that had a higher kind of carbon footprint than the other two, including the standard light frame. Can you comment on the reasons for that? Is there certain kinds of finishings and materials being used, floor coverings, etc., in the typical modular that has a kind of needs more frequent replacement or is lower quality or something like that? Just curious.
That's a great point. So it was a bit complex because I was trying to do two separate comparative analyses in all the same graphics. So the typical modular house was actually, I did an industry analysis and took literal models that are offered on the market of modular homes and chose the selected average. And so the resting model that I used is simply a larger square footage than the mass timber home and the light wood frame version of that design that I used. So it's just physically using more. If I had done some study that measured some level of intensity per square footage and shown that, the numbers there and the metrics would probably more accurately reflect closer, less polar, closer to the light wood frame version of the biomod design. So it's simply because it was larger.
Thank you.
I see that Tiffany put in, is anyone looking into fire resistivity and how that factors into the life of the structure in certain jurisdictions? Know where we can find that data. That's really interesting. Blaine is, in addition to this MS project, he's working on a similar project for the mass plywood panel house that that we're working on together with Tallwood, comparing that to conventional construction. So thinking about fire would be an interesting one, which we haven't thought about how those might be, how one might be more resistive and last longer than the other. I don't know, Blaine, if you found anything on that. We've been looking for drywall data, which is hard to find. But
no, I haven't been looking at the fire ratings at all. But I would imagine that in terms of getting out of the house before the whole thing's collapsed, my gut, this isn't on the record, tells me that a mass plywood home would stand up longer than a house made of sticks in a fire. But that's unofficial.
yeah, the next one from Martin, I'm just reading through the chat. Blaine, this is also what we've been looking at with the house, looking at comparing LCA numbers for standard construction with wood fiber insulation or mineral bonded insulation, aka wood wool cement, for whole wall assemblies and roof panels. Yeah, we've been, I mean, that is an important factor. I mean, the drywall is too, but when we just worked on the MPP house comparison, we were really thinking about more developer driven conventional construction. But yeah, it's certainly the insulation plays a big role, and thinking about some of these biogenic insulation materials would be really interesting. Blaine, I know you've been looking at that.
Yeah, for my personal project at large, I love comments like that. I enjoyed, I guess, the weakness of my study in that I did throw different insulations and finishes beyond the structural components. And so there's really a second message that's coming out as a byproduct of it, which is generating great discussion on what lightwood frame should be using. I'm not against lightwood frame. I think it's a great construction project or system. And if it uses the same biogenic materials that a mass timber system could, it would become much more competitive and environmentally sustainable. It would also use less fiber from a forest to build any given home. So there'd be advantages. And now there's discussions generated towards considering materials we associate with lightwood frame as an industry standard at whole.
Jonathan, I'm looking at your question, about carbon benefits and LCA signals being fairly clear, but with potential residents, with clients, I guess there have been nuanced preferences that can quickly stray from carbon as the primary driver. That can be an obstruction to advancement that plays a significant role in convincing them. That's our next presentation will be about the energy benefits from mass timber envelopes that we've been investigating at TDI. So basically, here's the preliminary findings are that they act like an air barrier. They're actually pretty much on par with an air barrier. A little difference between MPP, CLT, and the way you design the joint, but overall extremely energy efficient. So energy is a big driver. And I think the fire resistivity would be a cool one to explore a bit more too, if we could get some funding to look at that versus conventional. I don't know what other ones you might.
Well, yeah, I've been thinking about this lately because I've been trying to convince a few people that I'm working with that are age in place residents to be considering modular. And these are folks that I would consider fairly forward thinking in their approach. They're on a fixed income and they want to have an assurance that they're not going to be replacing a lot of things. And then as you start having this conversation with them about modularity and the benefits, they're all in. And then they're like, well, what about the refrigerator? And it starts to get into amenities and finishes and the adaptability of it. And it quickly strays off of modular for reasons outside of carbon. And it's a really urgent conversation to me. I have to like maintain and not get too stressed out when I'm having these conversations for their sake, because I'm trying to, shepherd them through a process, but I'm getting frustrated that I can't convince them of the benefits. And then I'm finding these kind of things that really have nothing to do with carbon that are wagging the dog, so to speak. And so I'm always on the lookout for new ways to convince people that this is the way, and also to solve problems that are easily solved, to make sure that these are very enticing opportunities for people.
Yeah, that's a great comment. Yeah, I think, I mean, designing for aging and how modular might work. I'm actually planning to teach a seminar on that. So I think that's a really interesting project that could be explored a little bit more with some of these modular designs.
It's a little off topic from the standpoint of just getting into the math on carbon, but I think that to me, it's really important to be able to make an argument so compelling that you'll put aside preconceived notions. And the people that I've been working with have already kind of bought in on the idea of an highly energy efficient home, et cetera, et cetera. But then there's all the other people out there that are potential champions, for lack of a better word, that are looking for a different type of thing and would have to be convinced of giving up, this idea about the American dream that's completely embedded in the psyche. So, well, good times.
Yeah.
I could say a couple things. When I was doing my project, I designed where almost every wall was made of CLT, aside from a single. Something I hadn't mentioned is that the efficiency in my design was driven by having plug-in modules where there was a single plumbing wall for any one bathroom home. And so you only have a minimum, or you could have a maximum of one light wood frame wall on the interior in a mass timber home. And what that really does is make MEP integration obviously pretty difficult compared to just having all of your interior walls light wood frame. So there could be a good balance between maybe the exterior shell is mass timber and the interior is light wood frame, or as architects, we're clever and we can design that system and have it promise that it's going to work without sacrificing any less level of its hidden from sight, and have everything work out. And then there's also a discussion of, I guess, biophilic design and the benefits you get from exposed wood, which is not everyone's cup of tea, especially if we're talking about mass plywood. It's a whole different level perhaps than CLT aesthetically. But I don't know, I really want it to work too.
I think, yeah, I mean, just really quickly on that topic, I think what's interesting about it is that everybody does love exposed wood. And then it's also about, well, maybe it doesn't work as the kitchen floor, or it doesn't work as the kitchen countertop, but I think those are easy to solve. Some of the challenges that to me are more kind of specific, even if we're speaking specifically of age in place, I just had that stuck in my head because I think you mentioned that. The convincing part of that is that the person that's potentially living in it isn't necessarily looking at it as a long-term economic kind of as equity or something. So that's another aspect to it that kind of informs the way they're thinking about it. And at the same time, the data that you kind of present about materiality replacements is super compelling, and I think needs to be really highlighted when comparing these, because I think that's a huge. So anyway, really great presentation, and I probably talked too much, so I appreciate the conversation.
Thanks, Jonathan.
Well, it looks like we're at 5 o'clock exactly, so it seems like a good time to end. There are no more comments or questions in the chat. And I just want to really thank Mark and Ethan and Blaine for presenting today. doing this great work and sharing it with us. I also wanted to thank Parker, my colleague at TDI, for organizing and promoting the meetups. If you're interested, we'll be, I think, scheduling something next month around. We've been doing a market study for the Pacific Northwest, looking in a lot of detail at current capacity and potential future capacity for mass timber in the region, and looking at everything from fiber supply to labor to um, sawmills, drying, all the kinds of supply chain considerations that would impact, the sector's ability to grow. And we've had through the Tech Hub, the Pacific Northwest Mass Timber Tech Hub, um, one of the grants, we've been able to bring on a team of consultants to do an analysis for us over the last 4 months. So they're wrapping that up, and we'll be kind of delivering the final product to us October 3rd. And we're hoping for a meetup sometime in October. So stay tuned for that. And we look forward to having everyone back on the Zoom.
Thank you, Ian. Thank you, Parker. Thanks everybody for joining us.
Thank you so much. It's been an
Yeah.
honor.
Appreciate it. Thank you.